Okay, we're going to talk about finding the area of regular polygons. Now, there's a lot to work through with this. We're going to try to take it slow, go through it step by step, so that you understand exactly what's going on and you know how to find the area of any regular polygon. Let's look at this example. Find the area of an equilateral triangle with apothem equal to 2. Now, remember, the apothem is the line from the center of our regular polygon to the side, and it meets at a perpendicular angle. So it's perpendicular, it meets at a right angle. And here our apothem is 2. And, well, if you remember correctly, the area to find the area of a regular polygon is equal to 1/2 times the apothem times the perimeter. So we need to find the perimeter of this triangle in order to find the area. Well, the apothem, what I see a lot of students do is they say, well, okay, I know that this is 2, and so if I continue the line up and just draw it straight up here, well, then that must also be 2, and so, yeah, so they say that that's 2 as well, so the height is 4, and then they try to solve 1/2 base times height. We can't do that, okay? That is not right. The apothem is from the center, perpendicular to the side. It's not from the center to the vertex. But in this case, we actually do need to use what's called the radius. The radius, which goes from the center, maybe we can just go like that, which goes from the center to a vertex. And so here's something that you need to know about the radii of a regular polygon. If we were to draw all 3, so we would draw one here as well. Oops, let me fix that a little bit. So my radii are going to look a little wonky, but that's okay. And there as well. The radii actually divide that central angle into 3 congruent parts. Right, so we have this angle here, we've got this angle here, this angle there, and another angle here. So all those angles are 120 degrees. Right, 120 degrees. Maybe we can make that a little clearer. 120 degrees. And so that's really important, and that's really nice for us because if this triangle in the bottom here, if that angle at the top is 120 degrees, then I have an isosceles triangle, right? The radius are going to be all the same. So since I have an isosceles triangle, these two are the same. This is the perpendicular bisector of that angle, so that means that this angle is half of 120, or 60 degrees. Which means that this over here, if that's 60 and that's 90, then this must be 30 degrees. That is. Let's see if we can hone in on that a little bit. 30 degrees. Okay, so that's one way you can think of it, is that the radius, so let's say that the central angles, which is those angles made over here, this angle right here is the central angle. There we go. That's the central angle. The central angle is 360 divided by n, where n is the number of sides. Oops, number of sides. So that's one thing that you can think about. Those central angles are 360 divided by the number of sides. Now, another thing we could think about is we know that the angle measure this whole angle right here of an equilateral triangle is 60 degrees. We know that that angle measure is 60 degrees. So, since each one of these angles is 60 degrees, the radius bisects that angle, right? This is 60 degrees. The radius bisects the angle. So that means this little angle over here is half of the radius. So maybe we just write, something you should remember is that radius bisects the angles of the polygon. The radius of a polygon bisects its angles. Okay, I know that that's a lot of information, so let's get into actually finding the area. Okay, we've got this triangle, right? 30 degrees here, 60 degrees here. Well, maybe we just solve it in here. Hopefully you can see it well enough in here. If this is 2 across from 30, well then 2 is my x. And across from 60, remember, is x root 3. We're using our properties of special right triangles here. So that means that since x is 2, this is 2 root 3. Half of one of the sides of this triangle is 2 root 3. That means that this whole side, and we can get this whole side right there, that's beautiful, is 2 times 2 root 3, or 4 root 3. Okay, so the one side length is 4 root 3. That means that the perimeter is 3 times 4 root 3, or 12 root 3. So then the area of the triangle is 1/2 times the apothem, which is 2, times the perimeter, which is 12 root 3. And so the area is equal to 12 root 3. 1/2 times 2 is just 1. So the area is 12 root 3. It wanted an exact value, so we're going to leave the square root there. Okay, let's look at one more example. Find the area of a regular decagon with radius 10 inches to the nearest tenth. So I don't have a decagon figure, so let's change this to let's change this to octagon. Is it octagon? Octagon? Yeah. I don't think it's octagon. That would be like an octopus. Yeah, I think it's octagon. Okay, I feel good about it. Find the area of a regular octagon with radius 10 inches to the nearest tenth. So remember, the radius goes from the center to the vertex. Let's draw that radius. Oops, with a line. Here's the radius. Good enough. Yeah, there, that's good enough. So the radius is 10 inches. Okay, now what did we just talk about? The radius, remember, bisects this angle. So we're going to actually create a triangle. Let's go ahead and create the triangle. Why not? We're creating this triangle in here. Oops. And it is, well, maybe I'll create the triangle. This is 10. And let's get the line and let's create it here just so it's nice and up and down. You could create any triangle, it doesn't matter. But this one, it looks like a 6. This one is nice and vertical for us. Okay, so we have an isosceles triangle. And there's two things you can think about here, right? We could find this angle, the central angle of our polygon. So remember that the central angle is 360. divided by n, where n is the number of sides. So in this case, that would be 360 divided by 8, which I believe is 45 degrees. How do I feel about that? Yep, that's 45 degrees. So the central angle is 45 degrees. You also could say, you could use the whole formula about finding the angle, each of these angles. Remember it's, let's see, 180 minus, no, sorry, 180 times n minus 2 divided by n. Remember, that's our that's the measure of an interior angle of a regular polygon. So in this case, that'd be 180 times 6 divided by 8, which, let's see, 180, I guess we can just do this math real quick. I'll use my calculator. I don't know if I trust myself to do it in my head, and it's okay to use a calculator. 180 times 6 divided by 8 is 135. So that's the measure. That's an interior angle. So that would be like right here, right? This is 135. Whereas earlier we found the central angle, which was 45 degrees. And then the radius bisects that angle, so 135 divided by 2 is 67.5, I believe. And if we check this, so that means that this angle right here is 67.5. If we check this, which we should be able to, 67.5 are 67.5 plus 67.5 plus 45, or 135 plus 45 equals 180, which is good because that's all of the interior angles of my triangle. Okay, so that was a lot, but hopefully you're seeing the different ways that we can find our angles given the radius. Okay, so since we know these angles, well, remember, we're looking for the area. We're looking for the area. Let's maybe change colors while we're working on area. We're looking for the area of this regular octagon. So the area is 1/2 times the apothem times the perimeter. So we don't know the apothem and we don't know the perimeter, but let's find them. We have this nice isosceles triangle right here. So if I drop a perpendicular line, oops, maybe make it a little more perpendicular, that's fine. If I drop a perpendicular line right here, then we can solve for that length and find the apothem, and we can solve for these two little lengths right here and find the length of a side, and then we can use that to find the perimeter. So let's draw this triangle. This triangle is going to look like this. We've got a hypotenuse of 10. We know that this angle is half of 45, so that's 22.5 degrees, and this is 67.5 degrees. This right here is 90 degrees. So we're going to use a little bit of trigonometry, it looks like, to find this. Let's go ahead and use this 67.5. The sine of 67.5 is opposite over hypotenuse, so let's call this x maybe, and we'll call this y. Maybe we can use a different color for y, just so that when we're finding those, we know what we're doing. Okay, so the sine of 67.5 is x over opposite over hypotenuse, 10. And if we solve for x is approximately, do a little squiggly line, x is approximately whatever the sine of 67.5 times 10 is. So again, you're going to need a calculator for this. The sine of 67.5 times 10. I'm going to look that up. You can't see this on your screen right now, I don't think, but sine of 67.5 degrees. Well, we'll just trust it. I think that we can trust it. So the sine of 67.5 times 10 is 9. We'll go to 4, because eventually we'll round to the nearest tenth, so I want to keep the hundredth for now. And then let's go ahead and find y, because we need y to find the perimeter. This cosine of 67.5, that's equal to y over 10. So that means y is approximately equal to the cosine of 67.5 times 10. So when I do that, I get 3.83. Got 3.826, so that's about 3.83. Okay, so now we know the apothem, and we know half of one of the side lengths. So this is the area. Go back to blue. The area is 1/2 times the apothem, which was x, 9.24, times the perimeter, which is 8, because I have 8 sides, times 8 times, my side length is twice of y, so 8 times 2 times y, which is 3.83. So the area, if you type all that into a calculator, the area is equal to 1/2 times, oh, that's 9.24. Sorry, not 9.25, that's 9.24. 0.5 times 9.24 times 8 times 2 times 3.83, which is equal to 283.1. And it gave us inches, so that's inches squared. And that's the area. Maybe we can write it up here. The area is equal to 283.1 inches squared. Okay, that was a lot of examples. Wow, my computer's possessed. That was a lot of examples. That was a lot of time, but I hope that these two examples help you make sense of how to find the area of a regular polygon.